everybody. My name is Soren Badger. Well, I guess maybe I don't care what you call me. Just call me either of these three names: Soren. Well, these two names: Soren or Arlo. Maybe Badger is fine, but I don't care. Anyway, welcome to talking about basically everything. Well, 99.9999998% of things, just to be described. We can't talk about everything. We might leave out a bit of computer, maybe a cracker crumb, but still, pretty much everything. Basically, we are made of things called cells, which are made of tinier things called molecules, which are made of tinier things called atoms, which are made of, which have nucleuses and electrons. Nucleuses are made of protons and neutrons. Oh, there's so much details, man. And electrons are, and protons and neutrons are made of elementary particles. And there are 18 different elementary particles of the universe, and they work together, but they work together to create the universe. And basically, in the Big Bang, these particles, these tiny particles, originated, and they assembled into the protons, and they assembled into the protons and neutrons, which assembled into nucleuses, which assembled into atoms 377,000 years after the Big Bang. And finally, these assembled into molecules, and they assembled into single basic bacterial cells, and life was created.
So that's a pretty broad sweep. I mean, a lot of things happened between those major events, yes?
Yes.
So if I understand correctly, what we want to talk about is there's the Big Bang,
Which is our main topic.
And then there's this period before the elementary particles formed.
Oh, the period before the elementary particles formed. That is called there's the Planck period, and then the inflationary period.
Okay, so what's the first period we can name after the singularity begins to expand?
The period right after the singularity expands is known as the Planck period.
Okay, how long does that last?
It ends 10 to the negative 52 seconds after the Big Bang, because
Okay.
it lasts 10 to the negative 52 seconds.
And what's going on during this Planck period?
Basically, the universe is extremely dense. It's been born, at least, but it's very dense, and it's very, very hot, and there was nothing but pure energy and more nothing. It's floating in a sea of no color, not even white or black. It's something that if humanity tries to imagine, then they will probably just fall asleep and they will not wake up for a few thousand years. Okay. Don't worry about it. We'll talk about it.
So what happens after the Planck period?
Then there's the inflationary period.
How long does that last?
I don't know.
Okay, and what happens during the inflationary period?
The universe suddenly undergoes some, we don't know what causes this, but some major bang of just a state where it comes from the size like millions of times smaller than a quark to bigger than the Milky Way galaxy and beyond. And then it just suddenly stopped. We don't know why it began, and we don't know why it stopped, or how, or when, but what we sort of do know when. But we don't really know why it just flashed out. What? I mean, the universe was still just energy. And then next, I think, comes the grand unification period. I don't know how long that lasted either.
What's going on? Well, first of all, can you say something about what actually was happening during the inflationary period? Why do we call it that? What's going on?
Because just a major expansion was going on.
Expansion of what?
The universe.
The universe. So space-time itself was ballooning out.
In the empty, I guess you could say nothing.
Strangely, it is now said that inflationary expansion was happening faster than the speed of light.
Yes.
And I'll just confess that I don't really know what that means, because to talk about a speed, you would be talking about a distance. And if you're talking about a distance, you're talking about traversing through space. But if we're talking about the actual expansion of space-time, strictly speaking, that's not moving through space. That's moving into some kind of non-spatial nothingness. So what does it mean to say that that motion is faster than the speed of light? I don't even know what it means to say that motion is fast or has speed at all. Can you help me out with that conceptual problem? Do you think you might like to actually sit in the chair as you do this?
Actually, humanity doesn't actually know.
Humanity doesn't actually know what's going on during the inflationary period? Or I was just trying to follow. I'm just trying to keep up. Okay, now, well, Arlo, so much for the inflationary period. We don't have much to say of use there.
Yeah, actually, the inflationary period is very unknown.
Okay.
We don't necessarily know.
We don't know necessarily much about it. All right, what comes after the inflationary period?
The grand unification.
Grand unification. And why do we call it grand unification?
Because all of the forces are into gravity and the electronuclear force. Which, since they're all merged, means that particles have not yet come into existence yet. So every time that something separates, every time that a force separates from a multi-force, I call it, or just a force when the multi-force is ended, then a new particle is created, and that particle is the carrier of the force. Since gravity was free from the singularity, when that happened, apparently when gravity was free from the singularity, the Big Bang was free. That may be the cause of the Big Bang. Gravity, for some reason, broke free from everything combined into just infinitesimal, just broke free, Big Bang. And so, the oldest known particle, well, it's unknown, it's theoretical. Stop. Just stop. It's a theoretical particle? And we don't. That's so it's the oldest particle that we can think of.
Graviton. Is that what you're talking about?
Yeah.
The graviton. As I understand, they haven't actually been detected as of yet.
No, but it's a theoretical particle.
A theoretical particle.
Just because just because we don't know what something is doesn't mean it can't exist. And its mass is also very low.
All right, so the unification period, the grand unification period. That's what you're saying. So what we think of as the four fundamental forces are really just two forces at that point: gravitation and
electronuclear.
Electronuclear. All right, and so.
And the end of that period is marked by the separation of the strong nuclear force with the electroweak force, resulting in just the electroweak force, strong nuclear force, and gravity.
We got three forces at that point. That's the end of the unification period.
Yes, but I would just like to comment something.
Yeah.
So since there are four forces, and the gravity force was one of the two forces that wasn't the only that was what we perceive it as a singular force, we could actually have there being two forces that are separated from gravity at some point. So in the next few thousand years, we could be having gravit and E. Okay, let's continue. Then we have the quark-gluon plasma period, which is apparently still in the primordial era, which is basically the Big Bang era, some people call it.
And how many seconds after the Big Bang is this?
10 to maybe negative 30 over 35, but under 40 something.
All right. So all of these, everything we've talked about so far is in this first micro fraction of a second after the Big Bang.
Yeah.
All of these different epochs are within that narrow slice of time.
Yes, but first I need to get big, because obviously the quark gluon plasma, as you can see, quarks and gluons were created. So since the strong nuclear force has been separated from the electroweak force, now there is the gluon, which is the carrier of the strong nuclear force. Gluon, the second boson, and finally and quarks. Now so basically quarks and gluons were in just the soup in this time of the early universe. Some of them were colliding and creating some unknown particle that possibly lasted for a very short amount of time, possibly as long as the Planck Period. And basically, the game of the universe starts here, as we know it. All of the different forms of quark originate, and the basic game of the universe that we'll talk about in episode 3, it really starts. Particles start working together, but some of the players are stuck in the electroweak force. But that's about to end it.
All right, so we are still in the first fraction of a second after the Big Bang. We're in this period where quarks are beginning to form,
Yes.
gluons, and there's some sort of just energy plasma. This a soup, and that's expanding.
Yes.
Quarks are starting to move around in there, but we don't yet have particles like protons and neutrons.
Yes, hadrons like those.
Hadrons.
Had.
Hadrons. We don't yet have the hadrons.
Yes.
We just have fundamental particles.
Yes,
But only a few of the fundamental particles. There will be more fundamental particles in the relative future. Is that right?
yes. So then let's jump forward. So 10 to the negative 7 seconds after the Big Bang, 7. So it's like 0.0000001.
Yep. Got it.
Subtract 1, 0.
Mhm.
1 seconds after the Big Bang, we enter a time where quarks are combining to form hadrons. These are the first non-fundamental particles. The quarks, three quarks do something that no quark has done before. Quarks have done before. They combine into a proton, a revolutionary step in the evolution of the universe. And they transmit gluons to each other, and
that's an activity of the strong nuclear force. Is that?
yes, and the electroweak force separates into the weak nuclear force and the electromagnetic force. So all the four forces, or rules of the universe, are laid out. The true revolution of the game of the universe on a subatomic level.
Yeah. So in that first, it's there right there at 10 to the negative 7 seconds after the Big Bang. We've now got all four fundamental forces.
Yes, they are the rules of the universe, and now the game can be played. We're leaving out the exception of the Higgs field, if you know about that, which is sort of a fifth force. If it reaches a very low energy state and releases a lot of energy and crashes into the low energy state, we could have a growing sphere of death, but we'll talk about that in a later episode.